Hello, and welcome to the video on the concavity of graphs of functions. We're going to determine where a function is concave up, concave down, and the inflection points where the concavity changes from up to down. Here's the definition from our textbook, from Anton's book. A function, if it's differentiable on an open interval, we say it's concave up on that open interval if the first derivative is increasing, and it's concave down if the first derivative is decreasing on a given interval. Graphically speaking, concave up means the graph is bent upwards. That means that the slopes of the tangent lines are going to increase. Concave down means the graph is bent downwards as we go across our interval from left to right. Let's determine the conditions for which we can guarantee a function will be concave up or down. Remember, if we have a positive derivative over an interval, that implies that the function increases over that interval. Negative derivative means the function decreases. What we're going to be concerned with concavity is the second derivative. Second derivative is the first derivative of the first derivative. So if that first derivative is positive, that means that function, whatever it is increasing. In that case, the first derivative is increasing, which tells us by definition that the graph of f is concave up, or we just say the function f is concave up. Likewise, if the second derivative is negative, that means the derivative of the first derivative is negative, which means the first derivative itself is decreasing, in which case the function f is concave down. Okay, this is the statement in the textbook. If the second derivative is positive over an open interval, then the function's graph is concave up. It's bent upwards. We say the function is concave up. If the second derivative is negative over a given interval, then the function's concave down. The graph is bent downwards. Let's take a look at a couple examples, graphically speaking. Here we have x squared. Notice the slopes of the tangent line. The first derivative is negative for negative values, but it's increasing. It's becoming less negative. Okay, again, using Paul Seeberger's applet, look at the slope of the tangent line over at the left as we trace from left to right. These slopes of the tangent lines and derivatives are becoming less negative. They're increasing. We go through 0 to positive values. The slope of the tangent line, the first derivative is positive, and it is getting larger. It's increasing. So the graph is concave up. The function's concave up. The graph is bent upwards. Here we have e to the x power. Notice all of the function values, or all the derivative values, are positive. The slopes of the tangent lines are positive, but they do increase as we go from left to right. The graph is again bent upwards. Here we have e to the negative x. Notice the graph is bent upwards. In this case, it's a little bit trickier. We've got to be careful. The function itself decreases, but the values of the first derivative increase. Right? The first derivative values, the slopes of the tangent lines, they are negative, but they're increasing. They're becoming less negative in this example. Next, let's take a look at some examples for concave down. Okay, here we have the graph of negative x squared. Again, this graph is bent downwards. Notice we see that for negative values, the slope of the tangent line, the first derivative is positive, becoming less positive though. Then 0 at 0, and then becoming negative, more and more negative. So the first derivative is decreasing. The graph is bent downwards. We say the function is concave down. Here we have an exponential decay flipped over the x-axis. In this case, the first derivative is positive all the time, but it's becoming less and less positive. It's decreasing as we go left to right. The function's graph is bent downwards. It's concave down. This one, again, this one's a little bit tricky because the function itself is decreasing, all right, but the slopes are also decreasing, right? They're becoming more and more negative. Going back to the last example, this one we have an increasing function. The graph itself is going up from left to right, but the graph is concave down, the function's concave down because the slopes of the tangent lines are decreasing, even though the function itself is increasing. The first derivative is decreasing. The last thing discussed in this video is that of inflection point. An inflection point is where the concavity changes from up to down or down to up. All right, there's a graphical picture for inflection points. Now, here are the steps to determine the concavity of a function. You want to first determine where the second derivative is either zero or where that second derivative might not exist. So if the first derivative doesn't exist, the second derivative won't exist at that point. So we want to know where the second derivative is zero or possibly where it does not exist. Most of the time, we're going to be looking for when the second derivative is zero. Then we're going to use our answers from step one, and we're going to test the intervals left and right of the numbers we find in step one. If the second derivative is positive, right, we're testing the second derivative. If the second derivative is positive over those intervals, the graph will be concave up. If it's negative, the graph will be concave down. We're also going to take note of any inflection points where the concavity changes from up to down or down to up. Let's look at one last example graphically and take note of an inflection point. Okay, so here we're looking at the graph of x cubed. Notice the function's increasing the entire time, but the concavity definitely changes here at x equals 0. We see it's bent downwards and then it changes to becoming bent upwards. The first derivative is positive for all non-zero x values, but notice for negative values, as x is increasing going from left to right, the slopes of the tangent lines as the first derivative becomes less and less negative. It decreases, or less and less positive. It decreases as we go from left to right. When we get over on the positive side, the first derivative actually increases as we go from left to right. So at x equals 0, what we see is we have an inflection point, right? The concavity is changing from concave up to concave down, or sorry, concave down to concave up as x is going from negative to positive values.